Now that we have this general setup of how symmetric ciphers work, what happens when Eve enters the picture? So the big thing here to think about is what are the assumptions we have to make, right? So we're going to assume that Eve sort of knows everything. Eve's listening in on the line. She's intercepting ciphertexts. And moreover, we're going to assume that she knows how the encoding and decoding works, that she knows how she knows what the encryption and decryption functions are. So, and that like, basically the only thing she doesn't know is the key, right? So the assumption here is, in terms of, we want to understand how secure a cryptographic cipher is. And so these are the assumptions that are generally made. We want to make the harshest possible assumptions and then see how secure it is. So Eve knows everything except the specific key. Okay, so right, by that I mean she knows the encoding and decoding process. Those are pretty standardized, so you would expect her to know that. The encoding and decoding scheme. She knows the encryption and decryption sort of functions. She knows the cipher, basically. She knows the whole cipher. You know, we said it was like plain text messages, ciphertext. You know, what sets this text, and the plain text and ciphertext come from the key space, the encryption function, and the decryption function. Oh, why does this C and this E look the same? Hopefully that's just distinguished between them now. So, i.e. how encryption works. In this specific cipher, right? But then even given all that, we want to see, can she, is it secure enough that even if she knows all that stuff, if she doesn't know the key, is that enough to prevent her from decrypting messages, her intercepted messages? I guess I should say she's intercepting all the ciphertexts. So cryptographers want to know, is this, even with all this, so cryptographers ask, given all these assumptions, is the system still secure? As long as she doesn't know the key. The specific key used to send the specific message. So let's explore this for a second. So for example, she can collect a bunch of ciphertexts. Could that ever just collecting more and more ciphertexts, is that enough to let you break the system? Let me give an example. So, or okay, first let me formalize this. And then let me give this example. So first, the first consideration, the first question to think about is the following. I guess what the first requirement, I guess I should say. As Eve collects a lot of ciphertexts, C1, C2, up through CN, it should still be hard for her to compute any of the corresponding plain texts without knowledge of the key. So it should be difficult. It should remain difficult to compute any of, or to find any of, I guess you would write it this way, the decryption function applied to each of the ciphertexts. It's hard to find any of this through the decryption of CN without knowledge of K. And you might think, well, of course it shouldn't be easy. I mean, it's there's some function. If she doesn't know K, how she can compute them? Well, let me give you an example where this breaks, because there's kind of a cool example. So an example where this requirement breaks. I guess I should actually add a second. I mean, I should add another caveat, or it should be hard for her to find K. Because obviously if you find K, then you can decipher all of these. You can decipher, because she knows the decryption function, she just doesn't know K. So so here's an example where this requirement breaks. Instead of using mod M, let's just take the set of plain text, the set of ciphertext, the key space. Let's just have them all be Z. And let's have the encryption function E sub K of M just be K times M. But here I'm saying no modding, just K times M. I mean, this might be fine, right? Why do we need the mods? Like, let's just multiply by a fixed number. And, you know, if these are big numbers and the messages are big and the ciphertexts are big, then, you know, maybe it's maybe this is secure enough. Maybe it's fine. Why do we need to mod? Well, here's why. Let's think about this. So Eve has this set, you know, Eve has intercepted let's just say a bunch of ciphertext C1 through CN. K divides each of these, right? Because this is C right here. This is the ciphertext. You just multiply the plain text by K. K divides CI for all I. Therefore, if it's a common divisor of all the intercepted ciphertexts, so thus K actually divides the GCD of C1 through CN. Right? And that's not hard to compute. If you have C1 through Cn, we've seen with the Euclidean algorithm that it's not hard to compute the GCD. It's, I mean, you can sort of do it pairwise, pair by pair, if you have more than two numbers. So, right. And then this is, and the more of these we collect, the smaller the GCD is going to become, right? Like K is a common factor, but, you know, maybe 17 also happens to be a common factor. And it just reduces your search space because like you're going to end up getting, GCD is basically going to be a small multiple of like the more C's we collect, or Eve collects, GCD, the GCD will become a smaller and smaller multiple of K over time. And so that gives you that way reduces your search space for K, right? And presumably if you collect enough of the ciphertexts, eventually they will kind of all be relatively prime to each other except for the common factor of K, and actually the GCD would actually just equal K. And so you can eventually find K. Reduces the search space. Search space for K. Right, because this is easy to the point is that this is easy to compute. So Eve can just start plugging in every time she gets a new ciphertext, just take the GCD with the previous ciphertexts, and that'll get smaller and smaller, and eventually it's just K, and she can try to divide ciphertext by K and see if she gets a plain text that when she decodes gives a message. That makes sense, right? So this actually shows you why modding is useful. Like modding creates this sort of mixing effect, right? This shows the benefit of modding. Because we're choosing, in this example, because we're choosing a unit mod, M, we're choosing something, basically the mod is relatively prime to K. It's relatively prime to K. So the GCD is lost. Basically, you lose the GCD information. Eve really loses the GCD information. So Eve can't get a handle on the GCD information, maybe is a way to say it. Well, let's say it a fancy way. She can't gain any purchase on the GCD information, which could lead to K. Right? Or the modding destroys the GCD information, maybe is another way to say it. This is the mixing effect of modding, and that's why modding is actually very useful a lot of times. Okay. So that's the first thing. The second requirement, that's the first requirement, is that, you know, you need to set up a cipher where just collecting ciphertext is not good enough to start to be able to break it. The second requirement is, and you can start throwing more and more requirements. I'm just going to talk about these two for now. But, you know, people are always trying to break ciphers, and there's people come up with interesting ideas of how to do so over time. We never quite know if something's secure. But, you know, we've started to collect over time these ways to think about things that we know certain things are bad, right? So the second requirement is what's called resistance to a what's called a known plain text attack. So Eve's collecting ciphertexts, right? And she might happen to know, and I'll give you an example of this when this actually happened in history. a plain text ciphertext pair. So so even if Eve knows certain plain text ciphertext pairs, she still can't recover the key. This actually happened in history, right? So historic example was the Enigma machine in World War II that the Germans used to send messages, especially to their U-boats, their submarines that were out hiding and destroying all sorts of anything being shipped across the English Channel and being shipped from the US to Europe, destroying boats. The Enigma machine. So one of the breakthroughs in cracking it, actually, they changed the key every day. So even when the Allies were able to find the key, they only had that day. They had to start over every morning. But here's the thing: every morning, the Allies realized at some point that they would start the day. The Germans would start the day with the same kind of messages. They would be like, an introduction and a weather report or something like that. And so they started to get a sense of like what the plain text should be. So they'd intercept the ciphertexts, the encrypted texts. But they started to have a sense, this is probably an encryption of just like a weather report or something like that. And it turned out that knowing that sort of the predictability of the kinds of messages that were being sent, looking at the ciphertext and the plain text and sort of, they'd guessed over time at how the Enigma machine worked. That was enough for them to break it and get the key for that day. And then they could start to, decrypt messages that were being sent. So this actually did happen in history, that the Enigma machine fell to a known plain text attack. And let me show you an example, because in fact, the mod example that we've had here, it falls immediately to a known plain text attack. So the math example is, sorry, I didn't write all that stuff out about the Enigma machine, but you can go Google it, look it up. Or I think you can watch that, what was that movie with Benedict Cumberbatch as Alan Turing? I don't remember the name off the top of my head, but you know what I'm talking about. I think it's talked about there. But our encryption, our example actually immediately falls to a known plain text attack. So this is bad. So our example where E sub k of m is congruent to just k times m mod, let's just say mod p for some prime p, right? And this is C, right? So we have k times m congruent to C mod p. Yeah. This is the plain text. This is the ciphertext. And, well, you can sort of see why, right? As soon as if Eve could ever figure out like, oh, here's a ciphertext of intercepted, but I know that they're sending this information, so I kind of know what the plain text is. So if Eve knows a specific pair, M comma C, well, we have an equation right here, right? And you can solve it for K. So then K is congruent to C times M inverse mod P. So Eve can find K. So Eve can find K. And that's bad. Right. Okay. So that just shows you that this is actually not a very good system, because you never know why. So for some reason, Eve might know what kind of message we're trying to transmit. Just as an example, right? Like if she recovers our example here, like even more specifically, we had M equals 4 and C was equal to 15, I think, right? When we did 4 times 11 mod 29. P was equal to 29 here. Well, then K is 15 times 4 inverse mod 29. But I think you can find pretty quickly that the inverse of 4 is 22, because 22 times 4 is 88, which again is one more than 87. So that is 15 times 22, which is 330, which is 290 plus 29 plus 11, right? 330 is 40 more than 290. 290 is clearly a multiple of 29. So that's congruent to 11 mod 29. And this, in fact, was our key. Okay, so that's where this gets hard, right? Like the idea is that Alice and Bob had to probably go to some work to exchange a key that they had to think about, like what's this key like that we're going to use. It's secret. We have to decide that almost in advance, because we can't just send it to each other because Eve will intercept it. We can't make ciphertext until we've chosen a key. And so this makes it pretty weak that as soon as Eve gets any plain text ciphertext pair, she can break the cipher and find the key. So what we'll be looking at is much more complicated situations, or this what's called public key cryptography, which is asymmetric encryption, which bypasses a lot of these problems. Okay, so that was a lot, but it's a little bit of a preview for what is coming next. I will stop.